Today, we are cracking open the internet's secret address book. This is the invisible system that makes our entire modern world work, the thing that connects your device to literally everything else online.
I mean, really think about that for a second. You type in a website, and in less than a blink of an eye, your phone or computer finds one specific server among billions and billions of others scattered across the globe. How on earth does it do that? Well, it all comes down to a really clever addressing system.
Okay, so let's get right into it. The key to understanding all this is knowing that every single one of your devices actually has two addresses. First, you've got the MAC address. You can think of this as its permanent serial number. It answers the question, who is this device? Then you have the IP address, which is more like a temporary mailing address. It answers the question, where is this device right now?
So the really important thing about the MAC address is that it's physically burned into the hardware. When a company makes a network card, they assign it this one-of-a-kind address. It's totally permanent, kind of like the VIN number on a car. It doesn't matter what network you connect to, that hardware always has the same name.
Now what's really cool is that this address isn't just a random string of characters. A MAC address is a 48-bit number, which gives it its unique identity. But it's actually split right down the middle into two parts, and each half does a very specific job. And this is where it gets really clever. The first 24 bits, that's called the Organizational Unique Identifier, or OUI. That part tells you who made the device. Is it an Apple product, a Dell, a Samsung? The second half is just a unique serial number that the company itself assigned. So with one address, you know both the maker and the specific device. Pretty smart, right?
Okay, so the MAC address tells us who a device is, but that's not nearly enough to find it on the huge, sprawling global network. For that, you need a mailing address. And that is exactly what an IP, or Internet Protocol address is. It's the where that lets data actually get from point A to point B.
An IP address is also made of two parts, and the analogy is super simple. Think of your home address. The first part, the network ID, that's like your street name. It identifies the local network your device is on. The second part, the host ID, that's your house number. It pinpoints your exact device on that street. Way back in the early days, the internet was carved up into these big neighborhoods called classes. Class A networks were absolutely massive, meant for just a few giant organizations. Class B was for medium-sized places like universities, and Class C was for thousands and thousands of small networks. It was a simple, if a bit rigid, way to divide up the internet.
But, what happens when that system isn't flexible enough? Let's say you're a big university, and you have a whole Class B network. That's like owning an entire city block. But you want to split it up into smaller private networks for different departments, like engineering, the library, and so on. How do you do that?
This is where the subnet mask comes in, and it's a brilliant little tool. It's basically a 32-bit number that acts like a filter or a stencil. Its only job is to look at an IP address and tell the computer, okay, this part right here is the street name, and that part is the house number. It just draws the line for you.
So how does it actually work? Well, without getting into the weeds of binary math, the subnet mask is just a string of ones followed by a string of zeros. When you lay it over an IP address, the ones basically highlight the network ID portion, and the zeros cover up the host ID. It's a super simple way for a device to instantly figure out what network it's on.
So, to make all those little neighborhoods, network admins use this technique called subnetting. What they do is they essentially borrow a few bits from the house number part of the address. They use those borrowed bits to create a new little section called a subnet ID. And just like that, you can slice and dice one giant network into hundreds of smaller, more organized, and more secure subnetworks.
Now, all of these systems, the classes, the subnets, they were all designed for the original Internet Protocol, IPv4. And because IPv4 was built on a 32-bit address, there was a hard mathematical limit to how many addresses could ever exist. Just under 4.3 billion. Back in the 70s and 80s, that seemed like an infinite number.
But nobody, and I mean nobody, predicted how fast the internet would grow. By the 90s, engineers could see the writing on the wall, so they came up with some clever tricks to delay the inevitable. But the clock was ticking. In 2011, the main global authority handed out its last big chunks of addresses. And then, in late 2019, the very last regional registry in Europe gave away its final block.
And that was it. The well had officially run dry. The original Internet address book was completely, totally full.
But here's the thing, this wasn't a failure.
Not at all. It was actually a symptom of the internet's unbelievable runaway success. The growth was just so massive, it blew past the original design. The engineers knew a much, much bigger system was going to be needed for the future.
So what was the big solution? It's called Internet Protocol version 6, or IPv6. And the change in scale is, well, it's almost impossible to wrap your head around. We jump from a 32-bit system with 4.3 billion addresses to a 128-bit system with 340 undecillion. That's 340 with 36 zeros after it.
I mean, just look at that number. It's so big, it's practically meaningless. To put it in perspective, there are enough IPv6 addresses to give a unique IP to every single atom on the surface of planet Earth and still have trillions and trillions of addresses left over. We are not running out of these. Ever.
Okay, I know what you're thinking. Those new addresses look crazy long and complicated. And yeah, they are. But luckily, there are two really simple rules to shorten them. Rule 1, you can drop any leading zeros in any of the blocks. Rule 2, if you have a bunch of blocks in a row that are all zeros, you can just replace that whole section with a double colon. You can only do that one time in an address though, so that way everyone knows exactly how many zero blocks you squished.
So here's the real takeaway. We've gone from a system built on scarcity to a new one built on almost unimaginable abundance. Now, every single device, every sensor, every car, every smart toaster can have its own unique public address on the internet. This shift from IPv4 to IPv6 isn't just a small upgrade, it's the bedrock for the next generation of the internet. The only real question left is, what are we going to build with it?